Welcome everyone to the SIO channel brought to you by Blockchain Capital, and welcome to the second installment of our Bitcoin Basics series of educational videos. Today I'm going to build on the previous video and show you exactly how the blocks on the network are created and assembled on top of one another to create the blockchain. Today you are going to understand why Bitcoin has such magic. The previous video, which explained the basic structure of the blockchain, should give you a sense that there's nothing extraordinary about it. But in today's video, you are going to get a better sense of the real magic behind Bitcoin, because you are going to get to see how it creates a system of trust between participants in a network, where no one needs to know anyone or trust anyone else on the network. No central party such as a bank, central bank, or a card operator such as Visa or MasterCard is needed to verify transactional activities between participants on this network. So without further ado, let's show you how this is done. Before we go, what I would like to do is just give you a sense of what we're going to cover today. So what we will be doing today is do a very quick recap of the previous video, so that hopefully you don't have to go and watch the previous video to understand the contents of today's. And then we are going to jump into the specifics of how we create the blocks and how we add the blocks to the blockchain. Just to manage your expectations, we are not going to go into the transactional details of each block. The specifics around the transactions, such as the transaction structures, the digital signatures, and so forth, that's a whole new level of complexity that we will reserve for future videos. In fact, that will be a lot more relevant when we start talking about how Bitcoin is programmable money and how we can program smart contracts between multiple participants on the Bitcoin network. And yes, Bitcoin can do smart contracts. All right, let's get started. In the last video, I showed you the basic blockchain structure, and the block is basically comprised of two major sections. Firstly, you've got the main contents of the block, which is effectively the list of transaction records and payment details between participants. And then you've got a header section that comprises of a number of fields that we didn't really go into. I also showed you how the blocks were cryptographically chained together. Specifically, I showed you how each block header contains a cryptographic hash of the previous block's header. And the cryptographic hash in particular was the SHA-256 hash. So in this particular example here, you can see that block 2 header contains the hash of the previous block header. Block 3 contains the hash of block 2's header hash. We also went into a little bit more detail where I showed you that each particular block header also contains a cryptographic hash of the transactions of that particular block. Let's just go there quickly. So in this particular example here, when you drill down into a little bit more detail, you will see that one of the fields in the header is a hash of all of the transactions in that particular block. And the main takeout here really is that you cannot alter the contents of any block without also having to modify all of the subsequent blocks' data. The other thing that we covered in the last video was SHA-256. Stands for simple hashing algorithm, and the 256 means that it spews out 256 bits fixed length output of data. And I showed you last time that when you just do a very small change to the input of this particular hashing algorithm, such as, for example, if you look at the screen, you take the exclamation mark out of the word hello, the resulting output is very, very different. These outputs here are in hexadecimal format. I'll show you later the binary format, but the point is that SHA-256 produces seemingly random outputs. They are actually deterministically random. It's a very, very cool feature of SHA-256. And effectively it means that you cannot really predict what the outcome will be. So not even by process of simple approximation can you try and attempt to figure out what the output will be, because the slightest change to the input of this particular hashing algorithm just produces a completely undeterminable output for you, okay? And you will see later why that is relevant. And then lastly, we ended off the previous video by saying that what we now need is a way for everyone on the network, the Bitcoin network, to have the same set of blocks that presents the single version of the truth. We did not cover how that happens, and that is now what we are going to be tackling in this video. Okay, now this is where things become really interesting, because the Bitcoin network is not supported by banks or any other kind of backbone that provides the trust that we are accustomed to. Instead, the Bitcoin network is a very clever network of distributed computers, we call them nodes, that can be run by anyone without needing permission to access this network. It is not like the enterprise blockchains I referred to in the previous video, where permission is required to participate in those networks. Those enterprise blockchains are also sometimes referred to as permissioned blockchains. Not so with open blockchains like Bitcoin and Ethereum. Anyone can download a copy of the blockchain onto their local database. Anyone can download the Bitcoin Core software and start validating and mining blocks. Anyone can install wallet software and begin to send and receive Bitcoins. It's a completely open system. But because it's an open system, the issue of trust is one that we have to deal with. Because anyone runs a local copy of the blockchain, it is quite conceivable that they could tamper with the blocks with the transactions in one of their blocks, where, for example, they indicate that they've made a payment to you that did not actually take place. All they need to do is convince the rest of the network that their block of dishonest transactions are the right ones, that the rest of the network has to believe and build on top of. So how do we solve that particular problem? Let's quickly go back to full screen mode and just talk about this with a little bit of visual aid for you guys. So imagine that we have a global network of participants on the Bitcoin network, and we have transactions being generated through all of the participants that are sending Bitcoins to one another. How does everyone trust that all of the transactions are assembled into blocks, recorded in the same way, and that the right blocks eventually are created so that every participant on the network is able to add the same block of transactions to their local database with complete surety that what they have is legit? Well, here is how Satoshi approached this particular problem. The first thing we do is we make the process of creating the blocks difficult, very difficult. But we do it in such a way that anyone who is trying to cheat the network by producing and getting the rest of the network to agree to a block of dishonest transactions finds it even more difficult to do so, to the point of being impractical. What we do is we create a system whereby any individual or group of individuals who decide to collude must effectively battle and win a computational war against the rest of the network in order for their version of transactions to be accepted by the rest of the network as the official set of transactions. It is actually quite genius. Now, more specifically, how do we do this? And this is where this particular diagram starts bringing the detail behind this. out of all of the different blocks and chains of blocks that individual participants on the network could possibly create, the network chooses to trust whichever chain of blocks required the most amount of computational work to create it. The Bitcoin network requires that each node that produced a block prove that a significant amount of computational work was invested in the creation of that block. And this is to ensure that untrustworthy peers who want to modify past blocks have to work even harder than honest peers who only really are interested in adding new blocks to the blockchain. So now I'm going to show you how this works, and you are going to see why SHA-256 is so relevant. Recall in the previous video, I showed you what happens if I put my name Erlen through the SHA-256 hashing algorithm. I showed you the hexadecimal format that will be produced, but here I've included the binary format as well, 256 bits. And then I also showed you what happens if all I do is add a full stop to my name. Look at how drastically different the binary and hexadecimal formats are. Can you guys see that? Now the other key thing about SHA-256 is that it is a one-way function. There is no inverse function for it. In other words, there is no function or algorithm that you can use to take a hexadecimal or binary output, feed it through the algorithm or function to produce the original message that SHA would have been able to take to create this particular hexadecimal output I was just referring to. So just to illustrate what I was talking about, if I said to you that here is a binary or hexadecimal output, and I asked you to determine what this input needs to be that you put into SHA-256 to create this output, there is no formula or algorithm that you can use to do that. You literally have to try different combinations of characters and numbers to try and determine whether they match the output that you want the corresponding input for. So you literally just have to try and try and try again. As you can see, with each and every single try, you just produce a very different output, and that output is unpredictable. Okay, what I would like to do now is just go into the details of the block header. Have a look at this. This field, the nonce field, is actually crucial to the whole operation of the creation of the blocks. Nonce is basically a number that is used once. So let's see how that works. What if I told you guys that I found a special number, this number highlighted by the red rectangle? What if I told you that I found a special number such that when I put that number into the nonce field of this particular block's header, and I run this header through the SHA-256 algorithm, that it creates a binary output, the first 30 digits of which were all zeros? How hard do you think it would have been for me to find this nonce that gives me 30 leading zeros in front of the hash? Well, for a random message, the calculation will show you that it's roughly 1 in a billion. So it is quite conceivable that I would have had to gone through a billion tries before I find the right nonce that gives me a hash that has 30 leading zeros. And this is one of the very important fundamentals with regards to the creation of blocks in Bitcoin. More specifically with Bitcoin though, we don't typically talk about the number of leading zeros. What we do is we talk about something called a difficulty level or a target threshold. So really what we need is for the hash that is produced to sit below this target threshold, which in simple terms really means there are more or less leading zeros in front of the binary output. This target threshold value is one that is set by the network, and the network will set a target threshold such that it takes on average one node 10 minutes to produce a valid block. And by valid block we mean a block that has a nonce that when inserted into this header produces a hash output that is less than the target threshold. So the network will set a target threshold, and all of the nodes that are mining blocks will effectively have to loop through all kinds of numbers until it finds the nonce that creates the hash that has a value below the target threshold set by the network. And it is an iterative process. So as you can see, determining the nonce is computationally intensive. Of course, once you find the nonce, verifying that it is the right number that gives you the desired hash output, that is very, very trivial and quick, and the rest of the network can validate that very, very quickly. This nonce is also sometimes referred to as a proof of work. The fact that you have a nonce proves that you have gone through a computational process to find it. And proof of work is also the term that is very often used as the description for Bitcoin's consensus algorithm. So it's a useful term for you guys to remember because a lot of the technology experts out there have opinions with regards to different types of consensus mechanisms. There are things like proof of stake, delegated proof of stake, proof of authority, proof of elapsed time, and proof of all kinds of other stuff, which the technologists have a lot of fun trying to get into. The nonce, or the proof of work that the Bitcoin miner was able to find, is very strongly tied to the transactions in that particular block. Now what this means is if you even make the slightest change to any of the transactions in the block, you would have to find a new nonce to create a hash that sits below the target threshold set by the network. And you'd have to go through the process over and over and over again until you find a nonce to yield a header hash that sits below the target threshold. So again, this is computationally hectic. So now that you know how the nonce is used in the Bitcoin network, let's just take that back to our previous set of blocks and see what the implications are. In this particular scenario, if I had to adjust the transactions in this particular block, effectively, I would have to run through billions of numbers again to create, or rather to find, a nonce that would yield a header hash below the network's target threshold. And that would mean you have now created a new hash using a new nonce, and the hash that is stored in the subsequent block, having now being different, requires that this block's nonce be determined from scratch again. And the same thing with the next block. All right, can you guys see how computationally difficult this whole thing becomes in terms of creating blocks and having to update the content of subsequent blocks if you made even the tiniest change to one block set of transactions? So we have now just demonstrated how Bitcoin uses SHA-256 and the idea of a nonce to make the creation of a valid block exceedingly difficult, and all the network needs to do is agree on a difficulty level, which it does by setting the target threshold in the headers of blocks. And by setting their target threshold, they then get all block creators to compete for determining the nonce that will make a valid block of transactions in other words, create the desired hash within that 10-minute time frame. And so again, guys, I know that I'm being repetitive here, but hopefully you get to see that if anyone tried to tamper, if there was a fraudster trying to tamper with the transactions in the network, they would have to redo all the work and race against the rest of the network. Okay, not only do they have to find the nonce for their dishonest block first, they need to be first in determining the nonce for the second, third, fourth, fifth blocks thereafter to convince the network that their chain is valid. Recall earlier we said that the network will trust and defer to the longest chain, the chain that has had the most amount of work put into creating it. All right, now what I want to do is quickly just take you through some more visuals, because visuals are always great. Have a look at this. We have transactions being generated and payments being made between people on the network. These transactions need to be assembled into a block. Now the additional piece which we didn't show you earlier is that now of course you need to find a nonce that will make the header of this block yield a hash that sits below the target threshold, right? And to do this, to find the nonce, you are going to have to just go through many iterations of numbers until you have found the right nonce. Okay, once you have found the right nonce, you can then tell the network that you have found a block. You can broadcast this block to the rest of the network. They can validate it very easily. They just simply run it through SHA-256 and they say, great, this is a legitimate block, and then people will be able to take that block and add it onto their chain of blocks. This is the way that we maintain integrity between everyone in terms of the copies of the blockchain that they have. Now, let's say that, and this does actually happen, we have two blocks being mined at the same time within that particular 10-minute time frame. Which block does the network trust? Well, normally, like I said, you would choose the chain that is the longest, the one that has had the most amount of computational effort put into creating it. But it does happen that sometimes you will have blockchains with conflicting blocks that are of equal length. Then what do? Well, very simply, you just wait, okay? And you wait for more blocks to be generated. Now, for this particular scenario, let's assume that this miner here, where I'm showing you with my mouse, is a what we call a bad actor, or someone that is trying to cheat the system. And then these here are all of the other miners on the rest of the network. Let's say this bad actor created a dishonest block of transactions and has a blockchain of equal length to the rest of the network. So what do? Well, we just wait for more blocks to be produced. And if this particular miner happened to have a superior amount of computational power and a bit of luck, they might be able to create the next block on top of their fraudulent block before the rest of the network does. Okay, and we wait again. This time, someone else in the network happens to have the luck and the computational power to create the next block before our fraudster was able to. And we wait again. And in this particular case, someone else again on the network managed to find a block before the fraudster did. And we wait. This time our fraudster got lucky and he was able to build, or rather create, the next block on top of his fraudulent blockchain before anyone else has, and we still have a tie. And so the process continues. The process continues, and because it is so computationally difficult to create the blocks, as we have shown, the odds that a fraudster is able to continuously beat the rest of the network and continuously be the first one to mine a block ahead of everyone else so that his block is able to be added onto the blockchain, the probabilities just become exceedingly small. All right. And what happens is eventually the network will discard the shortest block chain that they are hearing during the broadcast process. Okay, so hopefully this is starting to make sense for you guys. Some of you may have heard about the fact that we typically wait for 6 confirmations or wait for 6 blocks to be mined before a transaction can be considered final. And now you understand why, because the network just waits and waits until 6 block confirmations are completed, or 6 blocks have been mined, and the transaction then can be considered as completely final. So what have you just seen here? We have basically found a way to reach consensus about the legitimacy of blocks on a decentralized basis. There was no one individual that said my block is the right one or these sets of blocks are the right one. It is a process that the whole network adheres to, and by adhering to this particular process, legitimacy can always be trusted on. The important thing though, guys, is that this decentralized consensus reaching mechanism depends on the degree of decentralization, not the degree of distribution. So the more decentralized the mining power of the network is, the stronger and the more secure the network is. This is why Bitcoin, after 11 years of operation, has become the strongest, most secure, the most impenetrable network on the planet, because it has had time to grow. We've got thousands of nodes sitting on the Bitcoin network right now. So the magic comes from the degree of decentralization, not the blockchain. The blockchain is just one small element of what makes Bitcoin tick. And the analogy that I like to use is you could consider the blockchain to be the equivalent of the wing of an aeroplane. But if the aeroplane is standing still, it's not going to lift, right? You need to get the aeroplane to start moving forward. And once you've reached a sufficient velocity, the lift generated is able to raise the aircraft off the ground. It's the same kind of thing with Bitcoin, whereby the lift can be construed as the immutability of the blockchain, and the speed that the aircraft reaches could be analogous to the degree of decentralization. Once the degree of decentralization is sufficient, then immutability emerges from everything working together. All right, so guys, that was a mouthful. I know we wanted one concept at a time, but hopefully this was engaging enough. And you know what? Just keep watching this video and put questions in the comment section if you are uncertain about anything. So thanks for watching, guys. If you're watching this particular video on YouTube, please subscribe to our channel. Hit that bell notification icon so that you can be alerted to when we go live. If you're on Facebook watching this video, please like and share this video with as many people as you can. There will be lots more exciting content coming through later, and I look forward to chatting with you guys again next time. Have a good one, guys. Bye.